Start again?
Yeah.
Oh, okay. So that's the last time we did, and we have the first equations and the universal variables, and that one is we're going to use this symbol Kc, capital Kc, and that one is defined by this, and the derivative of Kc over time we define as mu square mu over r. Okay. So here the Kc, if we look into this one carefully, it has a unit like the length square root of the length. Okay. So that is definitions, and with this definition we'll be able to simplify something. So let me call this equation 2. And the equation 1 to here in these sections are carefully labeled, and because I think our lectures will spend more than 1 lecture hours. So we're going to refer to those equation numbers later on pretty much consistently in the remaining lectures, okay? And the other one is the for the boundary conditions, for the initial conditions here is this. At time equal to 0 and Kc is equal to 0. We're going to use this one later on. So with those things in place, the first one I will put into a few sections. The first subsection is I'm going to relate Kc to our the positions R, and I think I have an A, B, C, D kind of subsections here. So the first question is to answer how can we utilize this universal variable to describe our distance. So here we can try is this. We conduct certain operations. So that means equation 1 divided by the equation 2 square. So simply I take the square on the equation 2 and then take the ratio with respect to equation 1 and we see what happens. So therefore here we have is, here is dr dt square from equation 1, and that one equal to minus, I simply copy the informations. And over the square of this one, so that is d Kc dt square, and that one simply equal to mu over r square. Okay, so this one we can further simplify, and that one, do this carefully, equal to minus p plus 2r minus r square over a. Okay, and on the other side, this one we can further simplify. Basically, this one is dr and d Kc square. Okay, so here we simply put the square into these kind of derivative symbols, we can cancel dt. So basically that it becomes like this. Okay? So therefore from here, let me check these things. So therefore we have is dr, d cos c, and that one simply equal to square root of that numbers. Let me put it. So here right now again, I take the square root on this and that and rearrange. So therefore here I can have is d cos c equal to dr and then minus p plus qr minus r squared over a. So we obtain this one on the right hand side. This is a derivative of the derivative is the normal derivative with respect to r, and the r in the denominator here, that is a square root, and actually that is the quadratic functions and with a square root. So basically the whole things we can check into the tables. And I look up the tables. I have a book, and I got it when I, as a sophomore, and that's been with me for more than 30 years. I found that kind of things, and then I can provide to you. So using that equations, and that equation is this. That is the for indefinite and ax squared plus bx plus c. And this one, under the situations, can be equal to minus 1 squared minus 8 x sine ax plus b. Okay, we can use this equation to simplify this one. And the simplification basically is this. Then that is integration constant and we can further write it up is this. And here we have utilized is P equal to A times 1 plus E squared. So we have this one, and here the C0 is the integration constant. So with these things ready, we can solve for R. And for example, with the two. This equation, I can divide both sides by square of A, and then take sine on that side. So here I can have the R being expressly. So here, therefore, we have the C plus C0 divided by square A equal to arc sine, and that is R over A minus 1 divided by E. So therefore, here we take R equal to A times 1 plus E sine cos C plus C0 divided by A. This is equation 3. Okay, so here we got our goal. We relate the cos C to R. So once we know the universal variables, then we can plug in and then we can obtain R. Of course, here we contain the integration constant. We need to determine that one. But that is the first step. And in addition, so the next step is for our Kepler's problems, we are not only concerned about the positions, but another important factor is time. So here I'm going to relate conceit to time, the time of flight. Okay. This one we can obtain from here. And our definition of the universal variable here, that is actually related to time. And right now we already have R, so basically we can start from these definitions. So I would say from equation 2, and let me rewrite the c dt by definition equal to mu over R. Then from here we can have these things here. So simply I rearrange, so therefore d c R equal to square mu dt. So here we have the derivative. I simply integrate on the both sides. So therefore here we have is and so here you can introduce R by equation 3, okay? So we introduce R by equation 3, and then I integrate on the both sides. So then we have obtained is delta mu, delta t equal to, again here I'm going to integrate on the both sides, and this one will take a little bit rigorous, but wouldn't be hard because integration on this side over c basically is equivalent is integration on sine, and basically convert it into cosine something. Okay, so that one is a c minus a e square a cosine. That is equation 4. Okay, so right now we have, if you wish, you can box this, but the box information is good enough, but not that useful because we still don't know the integration constant. In equation 3 and 4, we still have one unknown constant, and that wouldn't be so useful. Okay, so here we take a break and looking at what we have done. So from here, the most important information is equation 3 and 4. Actually, from equation 4, you can come up with it. That is similar to, for example, for equation 4 compared to our Kepler's problems. If you remember, say, let me make one example here. For elliptic orbit, we have is mu. I forgot that one. Something like this one, right? And equal to n minus e sine m. Am I right? Okay, whatever. So this is kind of similar patterns we've seen before in the Kepler's problems for certain orbits. And different orbits have a different patterns, but they're pretty much the same like this one. Then on one side is the delta t, on the other side is about the eccentricity. So compared to this one, again, here is the time of flight, and this one we can conclude at this moment we can guess, because C would be the certain things relating to eccentricity. Relating to eccentric anomaly. Okay, something like the rho, because C plate here could be something the rho like M or B or F we've seen before. Okay, so that is the one, before we proceed, that is the one, the feelings we can get. And once we solve for C, once we know the constant, then we can know the positions of that object in the orbit. So that is the information 3 and 4 provided to us. And the next one we want to go forward is to how to determine the integration constant C0. So here I would say in equation 3 and 4, C0 is to be determined. So that means that is still not useful. So we're waiting for this one to be solved, and then we're almost there. So in this way, the next subsection C is I want to show you how to determine C0. So I will keep. Once I erase this one, so you should have all the equations be written. So maybe later I just refer to the equation numbers. Okay. So C is determined. C0. And in particular, we want to express C0 in terms of our initial position and initial velocity. Initial conditions. Okay. Because actually this is a time-dependent problem. So we usually solve for integration constant. We're looking for initial conditions here. Here we have a few steps. The first one, I want to show. So which means I give you the result first, and then I show you the process why. E sine C0 squared A Okay, we're going to use this one to obtain our information. And so that is kind of the useful information. And let me say this is equation 5, equation 6. And y here is our scratch, the scratch, S-C-R-A-T-C-H, calculations to explain why this. Okay. And using equation 3, and from here, we can plug in the initial information. We rewrite equation 3, and equation 3 is R over A. I divide both sides of equation 3 by A, and then I remove the 1 to the left-hand side. So that one, this one can become like E sine, and C0, and over A. Okay, so equation 3 can be rewritten like this. So from here you can see we, for this case, we with the initial conditions, and initial conditions is at T0 and C equal to 0. That is from our definitions. And then we have R equal to R0. Okay, we simply plug in those informations to here. So therefore, equation 3 we have is the R0 over A minus 1 equal to E sine and cos C equal to 0, so C over A. Okay, so therefore, this one, we check this. Okay. Then we take in the derivative of equation 3, we see what happens. So we take the derivative of equation 3. So here, in these equations, R is time dependent, depends on which location. Basically, R is changing over time, depends on the movement. Okay, and A constant, E constant, and C 0 constant. The only thing dependent is cos C. When we do define the cos C is a time dependent variable. So if we do the derivative on this equation, it's very straightforward. We simply take the chain rule into sine and then chain rule to here. Okay? So here that is the result we have is this. And that is AE square A and times let me write it up first, see what happens. I think this one is the arranged result from the calculations. And let me double check our textbook, but I think this should be the right one. And in my notes, I skip a few steps here. Okay, so basically when we do the derivative, we arrive this one. And I think, again, I skip up the few detailed steps, but here let me take this one. So here we rearrange and I multiply R with R dot on the opposite side and divide by square UA. This one basically equal to E cosine. Okay. So with this form, then we with the initial conditions one more time, at time equal to t0 and c equal to 0, and then velocity equal to this. Okay, so here we plug in here. Let me rewrite here. So that means here. So we simply plug in R0, V0. Wait a minute. For this one, let me do a little further expansions here. For this one, I want to show you this one basically equal to R dot V. Okay, so R dot V and Y, and I give you the explanations. And if we take the polar coordinate systems, So say if this is an orbit and this is the focus, so this is our R. Okay, and R we can express is R. If let me take this is the ER, is so in polar systems we use the two unit vectors. So R can be expressed as the ER, and this is our velocity here, and V equal to sorry, let me do one more time. Erase this one. I put into tangential. So this is our focus, and this is the point. So this is our V, and this is our R. I think in the polar corner system, I need to check is this is our true anomaly, and this is our ER, and this is our E theta. Let me take this one. Okay. So under these situations, the R can be expressed by is sorry, I made a mistake again. The first one is correct. So this is ER, and this is E theta. So under this situation, R can be expressed by R times ER. Okay, and V in this case that can be expressed by R dot ER plus R mu dot E theta. Okay, so therefore from here the R dot V dot and basically is we can see that is R dot. Okay, so here let me replace that one equal to this, and so under these situations we plug in, so that would be equal to R V mu A equal to E cosine C0 A. Okay, so that means here we have the 6 equations. The 2 equations will help us on the continue to the next one. So right now, again, our goal is to find out, to determine the C0 in both the 2 equations. And with the things, and let me scratch, will that be okay? And I erase these portions. So right now, I want to expand this term, sine. So this one, if you like that one, we know this sine A plus B equal to sine A cosine B plus the cosine A sine B. Okay, we know that kind of extensions. So basically we can expand it this one and using these equations. Okay, and also expand. In equation 4, we have cosine. So I'm going to expand cosine. Using, say, cosine A plus B equal to cosine A cosine B minus sine A sine B. So here using is sine A plus B equal to sine A cosine B minus sine B cosine A. Okay, so simply we're using this kind of expansions, then what we will have is this. Once you expand it, then you can expect this expansion will contain the sine. That will contain, once you expand it, you should expect in these expansions that will have this term and this term there. That be okay? Let me do it one more time. Let me do it one for you. So for example, for this one, once you expand it, then here is a scratch. That will be sine x0 divided by A and cosine C0. Plus sine C0 cosine. Right? So once this is expanded, we have such things. And we're going to use this one from here. We're going to use this one from here. In a similar way, once you expand the cosine, then you have a similar things. So after everything done, then we can have the equation 3 and 4 be written like this. And that one has a long writing here. So let me write it up here. So here, after we expand it and rearrange, introducing 5 and 6 equations, then we have is this. R will be equal to A plus A this is equation 7, this is equation 8. So here the summaries, after those things, we obtain the equations 6 and 8. The two are the most important equations, and this one right now we can use. Okay, so basically the equation 6, 7, and 8, that is the representations of the Kepler's equations in terms of the universal variables. And so from here, we can look into the individual terms and carefully. In the meantime, let me double check any typo I copied to here. Seems nothing there. Okay. So in the two equations, how can we utilize the two equations? And you look at here, the A and this one, A and E are A is the integration constant, and this one, the universal variable, that is a 1. V is the only dominant variables in these equations, and R0, V0, that is the initial conditions. And initial conditions doesn't is we are given here. So basically here, once we know the initial conditions, we can solve for R in terms of a C, or we can solve for C in terms of R, vice versa, like this one. So here for the equation 8, that is our Kepler's define the time of flight. So here, for example, here, if we given the C's, then we can calculate for delta t. And that is what we define as the easy Kepler's problems. On the vice versa, if we are given time of flight, we solve for c, and c is in sine. Basically, this is the hyperfunction. And this one we have to solve for using numerical approach. So the same thing here, basically equation 8 is the universal representations of the three Kepler's equations we've seen before. Okay? So right now that is the summaries of the things. And just due to the formulations, and somehow we have to deal with such long, at the first time, be honest with you, at the first time to look at this one is weird, okay, very weird. And but once you get used to it, that's okay. And now for this case, basically here you can see all the informations are involving is this one. C divided by square A, and also have C. So basically the two weird terms appears in all the equations here. And the you can do it directly using sine calculator using to calculate sine and cosine of something. But the follow-up to make the things complete and per our textbook, the people try to get a easier expressions of the two equations. They are trying to replace this term with additional equivalent variables. So simply they define is this. With this in mind, then the fourth point is we want to simplify the expressions, not expression, we want to simplify the look of the two equations. And so that is I put into these sections here. So basically here, the people think about this one is not so, in some ways, at the first look, it looks not so friendly, but in numerically, sometimes this expression it will give us certain troubles. So basically, people try to define this one as the square z. Okay, so here we want to re-express both equations in terms of z. Then here is the things. Defining z is equal to x squared over a. So, which means a equal to cos c squared over z. So we're going to have those kind of things replaced. So equation 7 becomes, we do this carefully, r equal to, we simply replace those things, and a will be replaced by these numbers. Okay, so a will be replaced by that one, and then the x over square a will be replaced by z. So that is the result here. you may ask me, it seems we introduce more complicated expressions. And usually to this point, before a few students have left, and they just cannot bear with the kind of things. We're almost done there, okay? So that's the reason I sent an email warning. Yeah, so, but you will get you will harvest the most essential part here. So why we have to do this, and since we have the two revised expression, it's become a little bit more complicated than this one. That is not what we want. But no, actually the people look at this one carefully, and they found is in the above equations, they contain the terms 1 minus cosine z divided by z, and this one more or less. The people play around a little bit more. They found the two equations basically essentially is the combination of the two terms. Okay. So they come up with additional. They come up with the new functions. They simply define this as the CZ, and to simulate, to mimic the cosine. And they simply define this as SZ, and to mimic the sine. Okay, so they introduce the two new functions. In terms of these definitions, then we can rewrite the two equations here. So let me come up with the 9 and 10. Those are the what we need. So therefore, here the R here, please leave a space. I'm going to write out something later on. So R can be rewrite into cos C square C, and plus, and C here is C over Z. Okay, I drop off the Z, and plus R0 dot V0 square mu cos C 1 minus Z S plus R0 1 minus dc. So here again, C and S, they are the functions of the things. For simple writing, I simply drop off the Z. Okay, so here C, S, C. So C, that means C of Z, and S, that means S of Z. Okay. So for R here, that basically is equal to mu dt and dx. Okay, so that is from our definitions. We can put that here. Equation 10 is mu over delta t. The two equations are our final destinations. So the two are the formulations using universal variables and to express the Kepler's equations. And right now, the cos C is our universal variables, and those functions S and C S and C are the new functions we defined through here. So basically, S and C, they basically is the function of cos C. So everything here on the right-hand side, at least on this here, showing basically there are essentially only one independent variable, that is cos C. Okay. And why we have to use the new defined C and S functions? Because the two functions provide us a very convenient approach once we do the numerical simulations. So why it's convenient? I think this one we can erase here. Then it gives you the certain properties of so here the properties we can utilize is this. CZ is okay, so in precisely the definition for z greater than 0 is this. If for z less than 0, then we have the different 1 minus cosine, happens cosine. Okay, because here we have to make sure there's no complex number out of the square root. The two definitions are very complicated, even no one can memorize that one. But by all means, the two will be expanded. That can be in a series of the expressions. And the same thing as z. For SD, we have a similar definitions, but again, numerically, I prefer is using this one. In my programs, and I simply use MATLAB to do this kind of the calculations to a certain number of terms, and that can be pretty much accurate. And for why I recommend you, if you like, you can try to make a note why I recommend you not to use these definitions. This definition have a trouble if we dealing with the value of z that is very small, approaching to 0. Then that would give us certain singularity issues. So it's always best practice, and in program is using the series expression. The series expression basically is well-defined expression, as no any issue will be induced. Okay, so using the two. That's the first note. The second note, if you be interested, then you should be able to find, if we take the derivative of equation 10, then that will become equation 9. You can give a try, and not required, but in this way, that basically the equation 9 and 10, they are both good. So the two equations are the one we're going to use, and we spent about 1 hour and going over the most, I would say, technical content. And Here, before we do the exercise, I want to convince you why the two equations are really the one universal expression for Kepler's problems. And let me give you a certain evidence. So E, I would say Y equation 10 is a universal expressions of Kepler's equations for three types of the orbits. Okay. Here we can do a little bit preparations. So we let me pick say the T0 is at perigee. So let's take the perigee as our initial conditions. So that means in this way the R0 dot V0 at perigee we know is always perpendicular. Is 0, okay, and also at perigee we define our initial conditions. Initial time is 0, and also we know the C at that time equal to 0. So basically, in this way, the equation 10 can be simplified as simple as this: mu t equal to x3 s plus rp x 1 minus ds. Okay, so here. So after we pick up perigee as our starting point, initial things, we can simplify this. Okay, so now I want to consider is parabolic. So in hyperbolic, we have A equal to infinity. That is the orbital element. So therefore, 1 over A approaching to infinity. And so therefore, Z is approaching to 0. Okay. So therefore, in this case, I would say SZ, once we have Z equal to 0, then we can have those numbers determined as Z simply equal to 1/6 and CZ simply equal to 1/2. Okay? So therefore, from here, these equations, and so these equations, mu t will be equal to 1/6 x3 plus rp times x. And then furthermore, we multiply 1p cubed multiply with the both sides of these equations. Then what we obtain is this: mu p3 t equal to 6x3 and 1p plus rp x 1p. Okay, and also for parabolic rp equal to p over 2. Okay, so therefore this one we can rearrange. This one becomes 6. So eventually we obtain is this one. if you compare our parabolic, then you can see compare that one we have is here we can tangent mu over 2, that is what we define as a b, and here that is cos c over the square p. So in this way, in parabolic orbits, we can relate the universal variables to be that is eccentric anomaly or true anomaly by these expressions. Okay, so probably today we stop here, and then coming back, I will give you another field of that two types of orbits in a way we can successfully build up the relation between how can relate the universal variables to individual true anomaly for each type of the orbits. Then we complete the old theories, and then we pretty much we can look for some kind of numerical issues. Okay. Sorry, that is not my fault. Stop, please.